Good morning, good afternoon, and good evening, and welcome to today's webinar hosted by NXP with our partners at IAR Systems. Today, we'll be discussing how to build the right level of security for your application. Today's panelists include Aaron Bouch, Senior Field Applications Engineer at IAR Systems, and Clark Jarvis, Security Lead for the MCU Ecosystem Team at NXP. During the webinar, you can type in your questions in the question box found in the GoToWebinar control panel on the right-hand side. We will address as many questions as possible during the live Q&A at the end of the webinar. In a few moments, I'll also be sending a link to view the presentation material should you want to download and follow along. With that said, I'll hand it off to Aaron Bouch from IAR Systems.
Thanks very much, Megan. Good morning, and thank you all for joining NXP and IAR as we show you a little bit about how NXP's processor family and IAR's security products can help enable secure designs that will protect your intellectual property and prevent overproduction regardless of how secure your manufacturing supply chain is. We'll talk about some of the drivers of security requirements, followed by a discussion of collaborative security and how NXP's microcontrollers can support truly secure designs. I'll then focus on IAR's security tools, which make implementing some very complex concepts simple so that you can bring your designs to production completely secured and protected. Finally, we'll provide a demonstration of how you can develop in a completely secure environment and send your encrypted designs to an unsecured manufacturing facility while maintaining complete control over your IP and preventing overproduction and rollback. Security means different things to different people, depending on their situation. For an individual, it may mean protecting your valuable financial and personal information. For a company building intelligent devices, it often is related to protecting the valuable intellectual property in their designs, as well as the reputation of the company. It's estimated that in the next 15 years, there will be approximately 1 trillion smart devices in our environment, with an impact to worldwide gross domestic product of over $5 trillion. As a result, security is one of the top concerns for virtually every company developing these devices. All connected devices are potentially vulnerable to outside attack due to their accessibility. We've all heard stories about clever hackers who've gained control of corporate networks through these vulnerabilities. Many people don't think of a coffee pot or a smart aquarium controller as an interesting target for these hackers, since these devices themselves are not very interesting or valuable. However, the key is to find the most vulnerable device on a network with other more valuable connected systems and break into the network there. Both of these kinds of devices have been used to do just that and ultimately steal valuable personal and business data from corporate networks. So why are companies so interested in security today? Aside from the fact that customers prefer and sometimes require products that ensure security, governments around the world are enacting legislation to ensure individual privacy and security. Many of these efforts have been in development for some time, and others have been implemented already. In Europe, the GDPR legislation went into effect in 2019, providing sweeping changes to how companies interact with their customers on the web and through devices. Many countries in Asia are driving their own security efforts, motivated by the need to protect consumers and industry. At the beginning of this year, California's IoT security law took effect with many requirements protecting users, such as forcing vendors to remove any default device names and passwords, so that a user cannot simply use the same password as everyone else on their network router, creating a simple access point to anyone familiar with the device. The U.S. National Institute of Science and Technology is making progress towards a national standard for security, which will incorporate many of the ideas of the California legislation and other best practices. To help companies deal with the complexities of this myriad of legislation and customer needs, a list of 13 best practices for ensuring security of IoT devices has emerged. The top 3 are prioritized as crucial for any device. However, by following all that apply to your design, you can ease the process of ensuring that your design will comply with the European GDPR, California IoT security law, and the emerging legislation coming in the US and around the world. It's worth noting that there are many stakeholders in every company working on implementing their own security strategy and implementation. The only new job function shown here is the Chief Information Security Officer. The other roles already exist in every company, and their responsibilities and interests in security implementation can vary widely. The CISO is responsible for ensuring that the policies and procedures are in place for the organization to deliver secure products to their customers. The CEO is interested in maintaining the value of the company through protection of expensive intellectual property and maintaining the reputation of the company's brands. The development manager wants to ensure that her team is not wasting resources supporting clone devices. In addition, she'll want a secure mechanism to provide field updates of firmware in a secure environment where third parties cannot steal or change the new firmware. And the development engineer needs an environment where the design flow is largely the same and familiar as the systems he's used for years without the need to become expert with the details of a new and complex technology.
All right, thank you, Aaron. As we look forward to kind of these different personas, right, and the concerns that these individuals have, what we wanted to do was provide a solution, a collaborative security solution that is brought by the devices available from NXP, along with the development tools from IAR systems to really create this secure development flow. The partnership that is established between NXP and IAR systems provides a secure solution that is targeted specifically at addressing these concerns. Alice, our CEO, is able to protect the reputation and monetary investment of her company by being able to secure the supply chain through the use of an HSM and enable protection of the company's brand through controlled policy management, all while leveraging the investments that she has in place with the supported development tools. Bob, our Chief Information Security Officer, is able to breathe easier knowing that the legislative laws and guidelines are being observed through use of the secure cryptographic key management, deployment of an immutable secure boot mechanism, and use of signed device certificate. On the development side, our manager and our engineers are able to efficiently develop a product and take advantage of the security features on the silicon device, such as JTAG restrictions, crypto accelerators, TrustZone support, and external memory capabilities, as well as supporting mass production programming flows and maintaining an established root of trust within the application. This collaborative security offering is made possible by utilizing the security features available on devices from NXP, like the Kinetis K series and LPC 55S6 products, along with a secure development flow that is enabled by development tools from IAR systems such as C-Trust and Secure Desktop Provisioner that we'll cover throughout this presentation. We'll next focus on some of the security features that are available in the NXP general purpose microcontrollers. At NXP, our solutions, our security solutions for general purpose and crossover MCUs focus on 3 pillars. There's authorized access, data protection, and monitoring of physical and environmental attacks. Now, there are many interrelated facets and dependencies between these pillars, but our webinar today focuses primarily on the authorized access section. We're focused specifically on the ability to protect the IP of the code, minimize the available attack footprint through debug interfaces, and being able to ensure that the code booting and executing on the device is from a known and trusted source. NXP provides the broadest range of ARM-based industrial application processors and microcontrollers, scaling across a wide range of performance capabilities with increasing levels of functional integration. The devices that we'll be focused on for this security webinar are primarily the general purpose MCUs within the Kinetis and LPC product families. IAR Systems has recently expanded support of its C-Trust IP protection and production control solution to include several additional MCUs in the Kinetis product family, the LPC55S6 series of devices, and will be releasing support for an I.MX RT crossover product, the RT1064, in the near future. Turning our attention specifically to the Kinetis K series of devices. The Kinetis K series of MCUs provides an ultra-scalable portfolio of devices with a wide range of optimized IP integration and a compelling balance of performance and power efficiency. Additionally, the Kinetis K series of devices includes a comprehensive set of hardware and software enablement. And the majority of the devices within this family are part of the NXP longevity program, ensuring manufacturing support for many years. Our collaborative security story that we introduced earlier relies primarily on a foundational set of security features that are available on all Kinetis devices. Some of these foundational security features are on-chip flash security and protection to prevent code and data from unauthorized access or modification. Debug port configuration, including the ability to restrict access of the debug port. A unique ID that can be useful for a device authentication, and controls to limit the boot sources to reduce the attack footprint of a particular device. There are additional features available on select Kinetis devices that provide for crypto acceleration, tamper detection, and secure key store, along with secure boot features that enable encrypted firmware updates and on-the-fly AES decryption. Looking now at the LPC MCU families, the LPC55S6X MCU family is a general-purpose, highly efficient Cortex-M33-based microcontroller, leveraging the ARM v8M architecture to provide new levels of performance and advanced security capabilities, including TrustZone M and coprocessor extensions. The LPC family of devices provides a compelling set of features, making it suitable for industrial and building automation applications with dual-core and power quad processing capabilities, consumer devices with USB or high-speed SPI and large SRAM, and smart home products with security, cryptographic modules, as well as low-power capabilities. The security features of the LPC55 MCU 100 MCU series is centered on the concept of a secure execution environment with features such as secure isolation between applications based on TrustZone, secure boot, cryptographic primitives, and secure storage, along with support for secure update mechanisms and authenticated secure debug access. Some of the specific security details featured on this device are Prince module for real-time encryption of data being written to on-chip flash and decryption of the encrypted flash data during reading to allow for asset protection. There's the AES 256 encryption decryption engine, secure hash algorithm, SHA-2 module supporting secure boot with dedicated DMA controller, physical unclonable function PUF, which uses a dedicated SRAM for silicon fingerprints that can be used to generate and store reconstruct keys, random number generators, 128-bit universally unique ID, and a secure GPIO. The LPC55 MCU series brings many breakthrough security features to the general purpose MCU domain, and the collaborative security partnership between NXP and IAR systems provides for a secure software development flow that enables the use of many of these features.
Thanks, Clark. IAR Systems provides a set of tools designed to enable addition of secure delivery of firmware, both at first manufacture and later, through secure delivery of firmware updates if needed. C-Trust is an add-on product that works with the IAR Embedded Workbench IDE to make the development of secure packages seamless for the software engineer. Along with our secure design provisioner, it enables a completely secure end-to-end flow from development through manufacturing. While connected IoT devices are an important focus of secure product development, even standalone devices and systems are at a risk of IP theft and unauthorized overproduction. Today, companies have complex manufacturing and supply chains with many points that are not under the direct control of the OEM. As a result, being able to enable the manufacturers and suppliers to provide their services while keeping tight control over your IP and production volumes is critical. IAR system security products, along with NXP microcontrollers, enable you to do exactly this. In order to keep control of your software IP and production control, one aspect that is needed is the ability to make your information useless to your supply chain except for its intended purpose, that is, to build your product for you. Fortunately, there's a large existing infrastructure and technology base for doing exactly that. These include symmetric and asymmetric encryption and decryption technologies, different encryption algorithms such as AEC, RSA, and ECC, which is elliptic curve cryptography, not an error checking technique. In addition, public key infrastructures and certificate and identity standards are all available so that we do not need to reinvent the wheel, but can use the best available techniques for the problem at hand. The graphic on the right shows the evolution of IAR systems tools from compilers, debuggers, and IDEs, which make up the core of our products, to include many additional capabilities. These include code quality tools, which perform static and dynamic code analysis, functional safety certified versions of our tools, and most recently, the addition of our security tools, which work seamlessly in the context of the existing Embedded Workbench IDE. On the left is a configuration screen for creating a secure boot manager as part of this design flow. In a secure development flow, we're simply adapting the traditional development workflow by adding some steps marked in light blue. By bringing these secure steps into the process, security from inception can be achieved. The dark blue steps represent the traditional development flow, which all software engineers are familiar with. You write your code, download and test it, and repeat this process until all features are implemented and debugged. At the front end, we add steps to create a secure boot manager and secret information, which implement the security policies of the company and device. Once a part is provisioned with this information, the process of download and debug looks and feels almost identical for the developer, as if they were developing without security enabled. However, in this case, every time they download code to their target, the code is encrypted and protected and checked and installed by the secure boot manager. In this way, the developer works in an environment analogous to how code will be delivered in production or through updates, preventing surprises when this is added at a later stage in development. This also provides the basis for delivering to manufacturing a completely encrypted and protected package, which can only be used by the SBM provisioned onto the target device. C-Trust is an add-on to our standard development environment, which provides the individual developer with everything they need to develop and debug in a secure environment. The developer can use target parts that have already been provisioned with a secure boot manager and security context, or they can produce a development policy provisioning package themselves if needed. Once the parts are provisioned, the day-to-day work looks very much like standard workflow without security present. When a design is released to production, typically a different security context and policies are used. For example, while the debug port would likely be open and enabled during development, this would be locked down and disabled when a part is provisioned for manufacturing. The manufacturing package is delivered to a hardware security module, or HSM, which then enables the provisioning and production of secure targets. This can be done with a high-volume chip programmer for large volume production. However, for small volume production and prototyping, the secure desktop provisioner can accept an encrypted manufacturing package from the C-Trust enabled IDE and provision and program the devices with complete production control. As mentioned earlier, this process is centered around a secure boot manager, which our tools produce with full source available for modification. To this, we add private and public key pairs to establish a chain of trust for encryption and decryption, as well as a software update policy that is implemented and enforced in the secure boot manager. The provisioning step can occur at one of several places in the development flow of a product. Initially, some number of target devices are provisioned with a development, boot manager, and security context. Once the development is complete, a different security context and secure boot manager are created to be provisioned into the production devices. As this diagram shows, this can either be done in a low volume setting on a device such as our secure desktop provisioner, or with an HSM and a high volume programmer. Here's an example of a view of what is contained on a provisioned part. The provisioning process places on the device the secure boot manager, as well as all secret information it will need to encrypt and decrypt data and ensure security policies. At the bottom of memory in red, you see the secure boot manager code, which is the first code to run on the processor at startup. In green, you see the user application area where the user application will run when it is present. Higher up in memory is an update area where an encrypted image can be loaded. There are also SBM data slots where key pairs are stored, which the SBM will use to manage its process. IAR's security tools also provide graphical management of the keys used to maintain a chain of trust. This enables the devices to be tied to appropriate information so that they can be identified by the OEM producer and so that the devices can recognize a trusted source for future updates. The way that IAR's tools manage the secret information used by the secure boot manager is through a mechanism called a security context. This security context includes the secret keys and certificates, as well as policy information to configure the secure boot manager. This provides an intuitive way to manage the complete data needed for secure products. Once a device is provisioned, it will run the secure boot manager at startup. The SBM will look for and install correctly mastered and signed images that it finds in the load slot in memory. Because of this, it is necessary that the tools be able to master the software image in a way that it can be used by a provisioned part. During development, code will be mastered using a development security context, and then remastered before production with a new security context appropriate for manufacturing. During development, each time you download to the debugger, the code is encrypted and mastered before it is loaded into the load slot on the target. The SBM then runs, and if all is well, will decrypt it and load it into the user application area to run. For production, the application is mastered and exported to a production programming device with a hardware security module, which has its own identity. When it's time for prototype production, C-Trust will be used to create a secure production package, which includes a mastered image, a secure boot manager, the needed security context, as well as identity information from the secure programming environment. In the case of the secure desktop provisioner, each unit has a unique identity and set of keys. The mastered package from C-Trust uses this, which ensures that the production package can only be used on the manufacturing device for which it was produced. From the manufacturing point of view, provisioning and programming parts is a simple process. First, secure production package produced by C-Trust is imported and checked that it is for this device. Next, between 1 and 4 target devices can be connected to the provisioner to be programmed together. The production package contains a number of devices authorized for production. So if only 110 devices are needed, the manufacturer will only be able to authorize and provision and program that many parts. Attempting to program more will fail. This is a schematic view of how the manufacturing entity would see the process. A secure production package is delivered to manufacturing at the left. The secure desktop provisioner is then run with its own application to import the package and produce the number of target parts authorized. So now we'll take a look at actually running the tools live on my machine. And I'll show you both what the development flow looks like from the developer standpoint, and then how to provision these things using the secure desktop provisioner. What we're looking at here is the embedded workbench running with C-Trust enabled. Now, the application that I have here is in fact an application from the NXP SDK. It's a FreeRTOS generic design, very straightforward. The first thing I'm going to do here is simply erase my device to ensure that there's nothing there and we're starting from a clean slate. Now, in order to create your own secure boot manager, it's quite simple. You can see here down at the bottom, I have 2 projects in this workspace. I have the FreeRTOS generic project, which is my application. I also have an SBM or secure boot manager project. The process of creating that secure boot manager is basically the same as creating any new project in IAR Embedded Workbench. So if I click Create New Project, you'll see that there is now a new selection in addition to an empty project, C and C++ projects, an externally built executable. There's now a secure boot manager project. And all you need to do is select that, and it will bring up a window asking you where you'd like to put your new secure boot manager project. And I'm just going to put it in demo SBM. I'm going to call it SBM. And it will create a new project with a fully enabled secure boot manager. Now, that will show up now in my environment. Unfortunately, I use the same name as my other secure boot manager. But just to show you, this project now, all you need to do is set up the processor that you're using under general options. So you would pick a device and search to the NXP devices that we're using. And once a device that is supported is selected, I can then go to the new security settings, enable security, and then set up the rest of the settings that I need. Now, this has already been done on my existing secure boot manager, so I'm going to start with that and take a look at what we have here. Now, if I look at my secure boot manager settings, we now have this security page for security settings. We've enabled security, and I've selected this context, which I've set up. So part of the process is I can click a new button, create a new security context, and connect this project to the security context. In that security context, as I mentioned in the presentation, is all of the information that I need to keep this process completely secure and protected. So here you can see we've got the memory map of where things are. In particular, here's the user application runs from 10000 hex, and the software update area, or the load slot, starts at hex 87800. So those are two useful points, because when I look at my application, I actually have to build the application to run at this location rather than at 0, which is now going to be where the secure boot manager runs from. In addition, I have settings such as version number check. So whenever I load a new version download to my target, it's going to check that the version has been incremented to be greater than the current version. I also have the choice of setting this at greater than or equal to the current, or no checking at all. However, greater than current is fine for our purposes here. So here within this graphical interface, I can edit various aspects of things that are logged by the secure boot manager, and my update keys that will be used when we are programming the devices. Now, there are two ways to provision the device. I can either, under the security menu, just select provision. And what that will do is it'll take the secure boot manager project as well as the secret keys, and it'll load it into the devices and then return. The alternative is I can simply do a download and debug of the secure boot manager on my target device. And by doing that, I'm actually enabled to debug the secure boot manager itself. And in particular, if I want to modify the behavior of the secure boot manager, I actually have all of the secure boot manager code here in sources, and I can make whatever changes I want. But here, I'm actually in the debugger. I'm at the mainline start point of the secure boot manager. And if I step through, it should print out some status information here of, it gave me the memory locations of where the load image is and where the executable image will run. And then it'll give me some status showing that there's no update present because I erased the entire chip. So I now have a provisioned chip with a secure boot manager and keys, but no application code. So I'm going to exit the debugger here and switch over to my application. Now, on a normal developer station, there's actually no need for them to even have the secure boot manager project there. I just did this for explanation. But what they would have is their application project here. And here, there are just a couple of things that are different in the application than it would be if I use my normal environment. So here, again, I've got security enabled, and I've got the enable button clicked. Here, I've got the same security context pointed to, as was used by the secure boot manager. So in this way, the application, when it's mastered, is going to use the proper keys from this security context to master it and then download it to the target. In addition to that, we use a different linker file than what would normally be used, because this will tell the linker to locate the project at the actual execution location rather than at 0 where it would normally run. So here, when I download and debug my program, what's actually happening is it's downloading into the load slot. It then resets, and at reset, the secure boot manager runs. And what you'll see is that when the secure boot manager runs, this is actually status information coming out of the secure boot manager, the same as what you saw before. However, this time you can see that it found the application, it installed it. It says installing version 3.00.103, update installed, running executable image, and it ran to my main first instruction in my program. So now I'm in an environment where I can do all of my normal debugging as I would on a typical program. And what you see here is, for instance, my FreeRTOS generic demo, which outputs messages telling me that there are a couple of tasks, one that sends a message, one that receives a message, another task, the event task runs occasionally. Down here, I've got a profile of the power consumption of the device. And here I've got all the interrupt activity. And down on my ITM window, I'm actually showing the task switch activity going on in this FreeRTOS project. So all of these things are available in your normal debug environment, are also available when you're working in a secure environment. Now, in order to get to the production model, when everything is debugged and ready to go, there's a few steps that need to be done to create a mastered image ready for production. So basically what we would do is we'd go to the security context on the project that I want to export. So I'll start by here and export the application. What this will do is this will master the application, but in a specific way that is to be used for transporting over to a production environment. So this mastered application, which I'll call program 1, and export. So this is very similar to the way the program is mastered when I'm just debugging. However, it's done in a way that can now be connected with all of the other pieces that the production secure desktop programmer will require in order to build the ultimate project. So now I'm switching over to the secure boot manager project. And here I also have a security selection called Export Direct to Production. So this is actually going to create the entire production package that's needed to be to produce products using the secure desktop programmer. Now you'll notice that I have a pop-up message here that says the security context settings are not set optimal for production. And the reason that that came up is because I'm using my development security context here just for convenience. I don't have a separate one, but as I said earlier, typically when you go to manufacturing, you'll create a new security context, you'll lock down the JTAG port, you'll probably lock down parts of memory, you'll do things differently than you did during development. So here, it's going to ask me for the trusted application package, which is the package that I just created, program 1. It wants to know the security context I used, and this is the same security context that I had in the settings window when both the application and the secure boot manager used. The OEM identity here has to do with the fact that this system, the secure desktop provisioner, has its own identity. So this is what is enabling us to ensure that this package can only be used on the secure desktop provisioner that has this identity. And it also has a passphrase that we'll use, if I can find it. It's on a different screen that you're not seeing, but I'm going to paste this in here. And now we take the certificates that were generated out of the secure desktop provisioner and a production count. So I'm going to set the production count at 3, and that's all that will be manufacturable. So the product name is going to be product 1, and the output folder, we'll put it in, will be our export folder right here. And we will export the whole package. So that should create, so successfully exported package to the location that I told it to put it in. So we now have that package. What we need now is our secure desktop provisioner software in order to program the device. So this is the application that you would use in manufacturing. Here, I'm first going to import the package that I just created, product 1. And it's checking the package to see that it is targeted for this device, and it is. So we accepted it. It's now available to build something. It now wants to know how many devices am I going to program. Now, my production run size, my authorized count, you can see here, I authorized that 3 devices could be programmed, and that was in my manager. I'm just going to produce 1 right now, and I'll say start production. So it's initializing all that it needs. Now, if I was going to build, say, 20 of these in this production run, I would put 20 there, and this process would only happen that one time. And then for the next 20 devices, I could have up to 4 programming heads here connected up, and I just say program connected devices, and I program 4 at a time. So in 5 cycles, I could program 20 of my devices. In this case, I'm just doing 1. So I'm telling it to program the connected devices. Notice there's also this auto programming mode checkbox, where if that was checked, as soon as I plugged in a new device, it would start programming. So here, production run completed, device requested 1, successful devices 1, failed none, initialization failure none. So we successfully programmed a device there. And with that, let me see if I can switch back to my other screen. So in summary, the joint work between NXP on their excellent devices, which provide the underlying hardware foundation for security, and IAR's tools that enable very easy turnkey development and delivery of secure products, you have a complete flow of everything that you need to build a complete secure development and manufacturing process using NXP's CPUs and IAR's tools. And with that, I'll turn it back over to Megan, and any questions that haven't been answered already, please do fire away.
All right, thank you so much, Aaron. Thanks for that great demonstration and presentation. We do have a few questions, so let's get started. The first one is, what is the difference between RSA and ECC? Why would I choose one over the other?
I'll take that. The primary difference, ECC is actually a relatively new technique compared to RSA. ECC, elliptic curve cryptography, actually uses an algorithm where the security of keys with much shorter lengths give you about the equivalent security of much longer RSA keys. So they're both very effective mechanisms, but for example, an RSA key with a 4K bit length gives you about the same security as an ECC key with about a 512-bit length. So particularly in tightly resource-constrained embedded systems, using the smaller keys settings where you have to store them in the RAM or the flash on your system, it can be a very effective way to store your keys. On the other hand, the complexity of the algorithm might be somewhat more difficult on either generating or decrypting the data. So there are trade-offs, but certainly from the standpoint of the key size, you would definitely go to the ECC world.
Okay, thank you for that. Another question is, can we secure data in transit to or from the device? And what about data stored on the device?
So as far as securing data to and in transit, the whole point of our mechanism is that the package that is delivered is completely encrypted. So it is in itself secure. Now, if you wanted to pass that through a secure channel in addition, that's fine. There's no problem, just as long as what you get out at the other end is the same data that went in the front end, which will always be the case with a correctly operating channel. As far as data on the chip, actually, yes, the encryption and decryption capabilities of the Secure Boot Manager are in fact available to your application as well through an API call mechanism. So the application can make secure calls to specific functions within the Secure Boot Manager when the application is running after the Secure Boot Manager has done its startup work.
Very good, thank you. We have 2 more questions and then we'll be able to wrap it up. So this next question is, how does the device know that the firmware it has is authentic?
There are actually two parts to that question. One is a new version that gets loaded into the load slot where it is still encrypted and signed. A new package would be signed by the originating OEM, and the device has the public key and its own private keys so that it can then check the signature of what was sent down and verify that it did come from a trusted source. And that is one of the checks that the Secure Boot Manager will automatically do before loading a new package into the execution space. Another check that the Secure Boot Manager does every time it starts up, even if a new application has not been loaded, is it retains certain signature information about the application that is already in the application slot, and it'll validate that nothing has changed it since the last time that it ran. So if any bits have been changed in the actual executable code in something that has been validated and loaded, then the Secure Boot Manager has the capability to lock down the system because of an invalid image that is now in memory.
Thanks, Aaron. And this one is in a similar vein and may have already been answered, but how does the device know that a firmware update really came from the OEM?
Right, and that is basically what I was talking about before, in that the package itself contains identifying information that was encrypted using the OEM's private key, and only the OEM has that private key. Now the device has the matching public key, and it can then decrypt that information and check it, and only information coming from the OEM with the originating private key will match in that way. So it provides the device a way to guarantee that it will only accept packages from a trusted source.
Very good. Well, thank you so much today to both you and Clark. We appreciate your time, and thanks to everybody who tuned in today. We will make these slides available in our community, and the recording will also be available afterwards on the nxp.com/training site. So later today, that should be available. All right, thank you, everyone. Have a nice day.